Alright guys, so today we're going to be talking about circular motion and gravitation. And the main concept of this unit is this idea of centripetal acceleration. So in order to understand centripetal acceleration, we're going to have to think of an object, perhaps a ball that is attached to a string, and imagine that you are causing it to move in a circle of uniform velocity. So, whenever this is occurring, we're going to have the object that's moving in the circle having a uniform velocity, meaning the magnitude of the velocity is going to be equivalent across any point along the circle. So this is just a segment of the circle. So if we're going to take a random point A and a random point B, the velocity 1, which represents this velocity here, is going to be equal in magnitude to velocity 2. However, velocity is constantly changing. This is because velocity is a vector, which means that it not only includes magnitude, but also has to include direction. And as you can see, the velocity is tangential to the circle at any given point. So therefore, although the magnitude of the velocity is equivalent no matter which point it is, since it is uniform velocity, or we are assuming it is, the direction is constantly changing, meaning velocity is constantly changing as well. So now, this idea of centripetal acceleration is that it is acceleration that points towards the center of the circle. And you may be wondering why that is. It doesn't really look like acceleration would be towards a circle. But as we know, acceleration is a change in velocity over the change in time. So now that we've established that our velocity is constantly changing, let's look at the change in velocity. We're going to have velocity 1 over here, this vector, and velocity 2. And in order to find the change in velocity, you'd form a triangle with these vectors, and this vector would point towards the center of the circle, and that would work with any 2 points along the circle. So now that we've established that the change in velocity is pointing towards the center, that means the acceleration, which is equal to the change in velocity over change in time, is also pointing towards the center of the circle. So now we know that centripetal acceleration not only points towards the center of the circle, but also that the velocity is constantly changing. So you can derive from knowledge of the circle, which you don't really need to know how, just know the equation. Radial acceleration, or centripetal acceleration, is equal to velocity squared over r meters per second and meters for the units. And also we're going to have 2 more main concepts. We're going to have this idea of a period, which is the amount of time for the object to make 1 cycle around the circumference of the circle, and the frequency, which is how many cycles happen in a second. And therefore you can be able to find the frequency with the period and the period with the frequency. And that just makes sense. Since period is the amount of time it takes to make 1 cycle, it would be equal to 1 divided by the number of cycles in a given second. So we also have this velocity is equal to 2 pi r over the period. This makes sense since velocity is distance over time, and in a circle, in an object moving around the circle, the distance would be the circumference of the circle, and the time for the object to move around the circumference of the circle is the period, as I discussed earlier for the definition. So velocity is equal to the distance over time, which is equal to the circumference over the period, which is equal to 2 pi r over the period. Now we can use these 4 different equations and solve some pretty simple problems. So here is a concept checked, or an example problem. Jupiter's circular orbit around the sun has a radius of 594,000 kilometers. It's actually much more than that, but just for example's sake, and a period of 27.3 days. Find the acceleration. So we're going to assume that the circular orbit is perfectly circular, though as we know through Kepler's law, they're actually more elliptical. But we're going to start off with our base equation of centripetal acceleration is equal to velocity squared over r. And you might realize that we don't have velocity, so we're going to have to substitute in something for velocity in order to find the centripetal acceleration. And we can plug in our 2 pi r over t, since we do have our period, and pi is already, we know what pi is, it's just a value, and r is also given. So that would be 2 pi r squared over t squared, since the velocity is squared, over r, which would be equal to 4 pi squared r squared. So r squared divided by r would just be r over r period squared. So now all we have to do is plug in some values in order to find our centripetal acceleration. So to get these accelerations equal to 4 pi squared r, which in this case would be 594,000 times 10 to the third meters. Remember, always convert to meters. And our period, which would turn out to be 2.36 times 10 to the 6th seconds. Remember, you have to have your correct units. So you plug these values in for pi squared times our 594,000 times 10 to the third meters divided by our 2.36 times 10 to the 6th seconds. And and actually you have to square the time. Remember, I forgot to square the time. So I'm going to do that one more time. 2.36 second e to the 6th squared. And you get a very small centripetal acceleration of 4.21 times 10 to the negative third meters per second squared. And all you had to do here was write our base equation, which you would memorize. Acceleration radial is equal to v squared over r. Determine which variables you have, which variables you don't, and just plug in for those variables and substitute in the variables. And also, if you're given frequency, you can find the period by this equation. Frequency is equal to 1 over t. So now we're going to move on to dynamics of uniform circular motion.